Hello, everyone. I'm going to try to talk about Yocto, systemd, and secure boot all in one talk. It could probably be 3 talks. So I'm mostly showing an integration and talking about integration problems. So it's really from a user's perspective. So we're not going to talk about the details a lot, but yeah, feel free to ask any questions. We should have time for that. So I'm Eric. My mail is down there. So if there are any questions later, just send me a mail. We talk about secure boot here at Connect, or in general, we have a lot of people working on fairly low-level things at Inara. So we very often talk about like the firmware and kernel transitions about secure boot. In this talk, that's not going to be a major topic. So we're mostly going to talk about the user space bits and how we can find some nice way to build an integration there. But yeah, what I'm showing here is still work in progress, so it's probably not a turnkey solution yet, but it's starting to shape up as a nice solution. There are, of course, many ways how you can build your system or what requirements you have. So here I'm just going to assume that we want some kind of GPT partition, want an EFI partition, we want some kind of read-only file system for our system. And we want some encrypted user data or some partition for encrypted user data that's sitting on my device and is encrypted with keys on this device. So of course there are many different other ways to do this, but the building blocks I'm showing here should still work, but yeah. So keep that in mind. I'm just showing the building blocks. It's up to you what to build from there. So I'm just going to go through a series of problems and then talk about the solution. So first problem here would be, now, how do we actually create this secure user partition? I mean, in general, the idea is simple. I just create some looks partition. But how do I actually tie that against my TPM? Because I want this to be like a per device key. I don't want to just share keys, have some key that's shared across my entire fleet. But I really want this to be private to this machine. And yeah, I can do this with TPM. But let's take a look at how that might be done today. So you start with a factory image that might already have some partition on there and some data that you might need to keep. So you might need to move that away. Then you create this partition on this device. I mean, this has to happen at runtime because we want to have a key that's specific for this particular device. So yeah, we have to create the partition, someone doing boot. We have to enroll the key somewhere in the TPM and then maybe eventually copy data back. So that's actually a lot of steps that we need to manually write. And there's currently no particular standard, like there's no Yocto script doing this for us. It's really something that a lot of people have to hand roll. I mean, it depends on how complex your system is, so maybe it's somewhat simpler, but yeah, it's stuff that you need to do. And there's an example that I pulled from TOS. So that's our reference distro. And this is really just doing the enrollment. I'm not an expert on this code. There are smarter people than me who wrote this, but it's just showing that there's a lot of code that you have to write, that you have to maintain. And this is security relevant code potentially, so it's stuff that you shouldn't get wrong. And it might be slightly simpler than this depending on your use cases, but yeah, it's not really ideal that we don't have anything there that can do this for us. Luckily, there is a solution to that. Some recent system, or somewhat recent, it's in there for a while, release brought a systemd-repart. And what systemd-repart can do, I mean, it's in the name, it can re-partition our disk and yeah, do this basically at runtime. So it boots up, checks whether our partitions are there, and just creates the one that are missing. So we have some fairly simple configuration format here. Yeah, so we just have the ESP, we have some user or system partition, and we have like our final, our user data partition. And then we just tell it, we want this to be encrypted. And then, this all does it for us. So all the scripts we no longer need, it does the same thing, but we do no longer need to maintain this. So I don't really care how we end up at the goal. We just want something simple, some turnkey solution that does a job for us. And the way it works is we start with our factory image that only has our system partition. Once we burn this into the device, we hopefully did the math, and there's some space left over. So that space is empty on the device. And on first boot, then systemd will match like the EFI partition against the first one. This one goes against the second, then it sees, oh, that one is missing. So it creates that one. We got the key enrolled, so yeah, and we get everything that we did with complex scripts before, which is with standard off-the-shelf systemd components here. Aside here, so maybe you spotted that here I only built an user into my system partition. There's some debate, there's some different solutions how you can do this. You can either have like your slash directory or everything under slash read only, then only have some paths that are writable. And that's the way how actually Yocto does it. If you use the read-only rootfs feature, then it will set it up, do some tweaks, like do some symlinks for files that need to be writable, do some overlay mounts. That works for like the basic system, but yeah, if you use, is anyone using this feature? You usually quickly run into problems where you need some particular program to like, I don't know, touch something in etc, want to persist your machine ID. So you really start just adding exceptions, you'll symlink stuff over, you do an overlay, all this kind of stuff. You probably add some persistent partition where you actually store data. So it's doable, but it needs some work to usually get it set up. So an alternative is to just use air as the only partition where all our like factory data or all our system data comes from. And it might be slightly weird at first, but we really got everything in there to boot the system. So this boots up, and then all the files that are missing are, or it's detected that all these files are missing, and it just automatically creates them. Systemd does this automatically. You don't need to do anything about that. And yeah, it's a fairly simple mechanism if you think about it. We no longer need to add all these exceptions. We just say everything from the system is under use air, and everything else is basically just use it. You should, of course, still stick to like best practices, have your configuration /etc, your variable data in /var, but yeah, this just makes it a lot simpler to integrate. And if you want to do factory reset, you just wipe the entire partition and it gets auto-created again. So it's just a lot easier to manage, in my opinion. Now, of course, well, we covered the encrypted user partition. How do we actually like secure or integrity check our use air partition? Here we're just going to assume that there are no secrets in there, so we mostly just want to do integrity checks. And the one solution to that is DM-Verity, and this is currently the solution that's best integrated with systemd. And not going too much into details here, but essentially we're building a hash tree. So in the end, you just have one root hash that can like give you the, or against which you can check the integrity of your entire system. Now, of course, just the root hash, anyone can generate that, so that doesn't give me like authentication of this image. So what you can do is like create a signature over this root hash, and then with this together, you can just, while you access the block device, do all the verification, and it's just fairly simple in the end. And under that, the data is just the usual data partition that ends up read-only. Now, again, how do you do this today? There are tools to help you with this in Yocto today. There's this DM-Verity image BB class that goes a long way. That helps you with doing all the DM-Verity building, but you still need to integrate that into your final image. And that's actually sometimes, it's something that you still need to do yourself again. So you probably end up like building your own intermediate image and then integrating that into the final one. So the way it works, it generates VKS include file that you end up including in your final VKS image, because you of course want to customize, you want to have your own partition. So it's certainly doable, but yeah, it's again, I'm talking about the user's perspective. The other solution I will show later is probably going to be a lot easier. So how could we do this together in the future, maybe? The answer would be, again, systemd-repart. Now, I earlier said that systemd-repart runs at boot. Now, you can also run systemd-repart at build time. So you can pass your like empty create size auto, and it can actually create a disk image for you. So you can integrate this into your Yocto build, and then you pass it some configuration data. For example, here it says we take the use air, place it into root. So this is just building a partition that only contains our use air. And it also has support for like automatically generating Verity images and signatures. So we just add these partitions. So it's a fairly simple configuration format. And then, yeah, we just call systemd-repart and we get an image that, looks the way that we sketched earlier. So we got the system partition added automatically, and we don't need to deal about any of the DM-Verity stuff inside there. Now, of course, we just build the image, how do we actually get this mounted? Oh no, my timer died. Okay. How do we actually get this mounted in the end? There is a way to just parse a US air hash, and then it will auto-discover where this partition exists, and we will mount it. And since we have the US air hash in the kernel command line, and hopefully the kernel command line is authenticated, then we can boot that. But if you do this in practice, then it's doable, but you have quite some dependency loops in Yocto. So it's not particularly fun. You can ask Mikko. He screamed about that a bit. But there's an alternative to that. And I have to start with the API group here. The systemd people and some distro people come together and started forming this group to develop standards that help with this kind of problems. And I'm not going too much into details about all of them. There's the link here where you can check it out. We are mostly going to cover these down here. But one of those is the discoverable partitions specification. Is it plural? I don't know. Maybe it's just singular. But essentially what it does is define some well-known partition UIDs, partition type UIDs, for particular types of partitions. So if we, for example, see these particular Verity partitions, then we know that there's going to be like Verity data, Verity signature, and if we see them, we can auto-detect them, merge them together, and then see, okay, we know that this is there, we can auto-mount it, and have this, can automatically read the signature. We don't need to configure anything, don't need to pass anything in the kernel command line, and yeah, basically, everything just works. Now, of course, just blindly doing this won't give us a secure system. Someone else can just build the same image, of course, but there are ways to like set an image policy that enforces that every image is authenticated. So DM-Verity, or also in looks, we authenticate the keys before we actually mount them. So yeah, I basically explained how that works. So we just discover it, all match it together. There is a specific format for that includes the DM-Verity root hash and the signature. And yeah, we can verify that. And once that all checks out, we know that this is an authentic image, and we just mount it. And then the user DM-Verity checks, ensure that everything is working. Now, of course, we still need to know which disk we actually should look on, which is a surprisingly hard question, maybe, because we don't really know which disk we booted from. But the short answer is there is this a standard that systemd defines. It's not your API, at least not yet, where they are basically just defining some IFI variables that are expected to be set. Those also help with like boot time testing or boot time measurements, because it's just about it's providing some information from the loader to the system later, and it's just some IFI variables that are expected to be set there. Systemd boot sets groups has some support for it, but it's not really full support. So it's mostly systemd boot getting tested against this, but maybe that will change in the future. Okay, that was easy. Then now, of course, we just can't unlock all these partitions and verify this user metadata before we actually run on the system. So we will need some kind of initramfs to do this work for us. It's not particularly hard. Systemd boot, systemd has support for this, so we just add systemd to our initramfs. We actually don't need much else, so they're currently working on trimming it down even further, but it shouldn't be too large. And yeah, we get the logic, but we need to guard our initramfs, of course, now, because that's the step that does all our security sensitive stuff here. So, but it's not the only thing. I mean, we got the kernel. The kernel is an executable, so you can already have that in IFI. It's not a big deal. But also the kernel command line, maybe some splash screen, device tree. So all these components we also need to verify. And there would be a way to do this with IFI. I know Elise here, he's favoring this solution, which is like an extension in IFI that allows you to like verify arbitrary files. But yeah, this is not part of the ARM system ready standard, and it's not part of like most x86 firmware probably either. So there's really no practical way to do that. So you only have the way to like verify binaries that you launch. And now my initramfs is not a IFI binary. But, well, why don't we just make one? That was what the systemd people thought. It's somewhat a practical solution. It feels a bit like a hack if you think about it first, but it works. So essentially what we're just doing, we are building one big IFI binary that has a stub before it. And then we just put all the data in there. So we put the kernel in there, we put the initramfs in there. They have support for device tree. We, I think, prefer to get that from firmware in the end. But yeah, you just put all the information in there. There's some well-known sections. Most of these are optional. They just provide some metadata, for example, systemd boot or so. But essentially what we just end up is signing this entire thing. And then we got an IFI binary. An IFI binary we can verify while launching. And we got that part of the secure boot closed. Now, of course, there are scripts to help with that. There's UKI build that helps to, yeah, we just parse it all the data, we parse it our keys, and then we will build it, sign it, and do it all in one step. And now, presenting a lot of hopefully nice solutions. Now, of course, there's a catch with that. Most of this is still a work in progress, and especially the Yocto integration is still lacking. As I said that Yocto read-only rootfs feature currently is working slightly different. So there's some integration pain there. Should all be solvable, but yeah, there is a bunch of patches that are currently sitting on the mailing list. Not all of them are actually receiving too much interest. So if you think this is cool, then maybe check those out and provide feedback or maybe review them. But yeah, there's work going on for UKI images, in general providing this UKI tool within Yocto, so I can just use it to build things. I sent a patch or an RFC to use systemd-repart at build time, which is somewhat radical idea maybe because we got Vic in Yocto. But I think if we just care about EFI or GPT disks, then I think this can be a fairly simple way to build fairly complex images with fairly simple configuration files. There's things that I didn't cover in this talk, but there are like system extensions in systemd. Some people are working on that. There are also some things missing or not completely implemented in systemd. For example, the auto-discovery that I explained earlier is not fully working if you use this USR approach. It only works for root file systems, but not for /USR, which is a shame. But yeah, you can work around it, but there's still some integration pain happening there. Then micro-fort against some race conditions in TPMs is not as easy to, in very early boot, discover that we actually have a TPM, for example, if it's running in Opti. So yeah, there is still a lot of integration issues, but I think my message of this talk is, I think that this is a fairly cool idea. And I know a lot of people are arguing about the specific details, like why do we do UKIs this way? Why do we do another thing that way? But I think, in my opinion, this is currently the most, or the closest way to us having like a standard turnkey solution to all this like user space secure booting. And I think that's a great value, and yeah, hopefully we can get the integration done and then have everything working there. Thanks to a bunch of people. Some are here at Connect, but also the systemd maintainers were very helpful, just providing feedback there. And that's the talk, so to take questions. So, wait.
So I guess it's less of a question, but more like what is going on as well that we're like on the founder side and also on the Qualcomm side. We're trying to integrate the UKI support. So like some of there's a quick-based patch that was sent in there. I think you can already create like UKIs for the images, but not like one thing that we still need to upstream is the ability to create UKIs while you're building the kernel recipe at the end of the process, not when generating the wiki image. It's just like one of the details. Like for example, we use OS3, so we don't actually use like the /user like as read only because like we get kind of all of that by like by default. And one of the things that I think there's two things as well, like for us that like we're still kind of struggling and we still need to find solutions is more like on the upstream side is for UKI, for OS3, we need a way, you know, like because OS3, like you need to give the hash a little bit like kind of DM-Verity as well. Like you need to give the hash, you know, like of the OS3 that you're building. And of course, like by, you know, like as a consequence, you need to change the command line, and then, you know, like it breaks the verification. So there's been discussion ongoing on how to send that information to initRD. But yeah, and let's see what else. And yeah, for the Verity integration and so on and so forth. And the other thing as well, if someone is planning on UKI, which is relevant, is like there's no support for multiple device trees at the moment. So there's open pull requests for that. Like you can specify one device tree, and you know, like that works and so on and so forth. But there's no, like, for example, easy way for you to have like a series of device trees, and then the firmware just pointing out which one you should be using automatically when loading.
Yeah. We don't do it through the UKI, but we just get U-boot passing us the device tree. So we don't particularly depend on this, and we actually leave it out of the UKI. But yeah, I think in theory it could be done in the UKI, but not sure if that's best. But yeah, it's certainly doable. And about UKIs, yes, all this build dependency thing is sometimes annoying, and maybe there are tweaks that can be done. For example, there's no way to also resign in UKI. For example, if you just do your usual Yocto builds with debug keys, and then eventually you want to do like a productive system signing. So yeah, I think there might be some ways to improve that situation. And yeah, if we can avoid putting like these hashes into the like kernel command line, then that helps. So that's why I showed this auto discovery. But that is also not fully implemented. Another nice thing with this auto discovery is that it might open the path to like version numbers and AB partitions. But of course, you don't need that in OS3. You're more flexible there. But yeah. Right, I acknowledge the problems. It's
yeah, and I'm curious, like, did you try like to integrate systemd on initRD as well, or?
Yes, certainly. Yeah. That's what we do, and that's what is doing all this auto discovery.
Okay, cool. In initRD.
Yeah, and I wondered if you want to build the UKI as part of the kernel build, then you end up depending on the initRD. Yeah. So I'm not sure if that's the best option. So yeah, it certainly needs to be simpler, but I'm not sure if the kernel build is. It should be hardwired to it, but maybe just. Yeah. Somewhere that it's more flexibly ordered, but yeah. Yeah. We got the second mic here.
Yeah, thanks. Maybe more of a comment. So I'm Mikko. I maintain the trusted reference stack Yocto distro at Linaro, and I'm doing exactly what you showed us as a demo. I'm trying to put it into practice. There's lots of issues. I picked up the UKI patches on the mailing list. Have a ton of patches on top of it, and I'm trying to upstream everything. So I've already, some of the bits and pieces are already there. One thing which is slightly blocking my work, I would like, I mean, when you submit something to the Yocto community, you want to have tests for it as well. And what is currently missing is a QEMU target with working UEFI firmware, which is capable of doing secure boot with a TPM device. That's missing. I mean, we could have real hardware. I mean, if we don't do it testing as well, it's difficult, or it's annoying to submit things which you can't really easily test in the community, so it doesn't break.
Yeah, you can, I think, like, you can use it with Intel. We test with Intel, basically, like using virtual TPM devices. And then on QEMU, like, you have a Tiano core-based implementation. And then, but yeah, on ARM, I don't think.
Yeah, well, we at Linaro have a bunch of stuff where we are, a bunch of targets where we are testing. We have, for example, QEMU with software TPM, it works. We have hacked it into the environment with Yocto, it works. The software TPM is taking from the Yocto build as well. That stuff works, but it's slightly ugly. Then we have real targets where we depend on certain, well, trusted substrate-based firmware, basically, where we can do UEFI secure boot, basically system-ready IR compatible with TPM. And sometimes with the real TPM, sometimes with the firmware TPM, which brings us a bunch of additional problems because it's not easy to detect in early user space boot if the firmware used a TPM device to do basically verifying of the firmware bits and pieces. And then for user space to know that, okay, I need to do something extra here. Load kernel modules, possibly even start tsupplicant as well in user space.
Yeah, so the libvirt ARM64 virtual machines actually do secure boot by default. So you can look into that to see which parameters you need to create a target in Yocto. So if you download a distro for ARM64 that doesn't do secure boot, by default libvirt will not boot it because it enables secure boot by default.
Okay, I need to check into that.
Yeah, if you check on Debian, for instance, if you create an ARM64 VM, then it will use secure boot by default.
Oh, that's interesting. Cool.
Close them. So we're actually trying to do that. We're trying to get a trusted application in running opti to expose exactly FTPM towards so I work on the Parsec project. I'm trying to get it to expose it in an FTPM and on an IMX8 Mini, and it's really messy. There's a lot on the kernel on the MX8. Let's say kernel kind of the branch. There's a few patches there that are existing. Let's say, for example, in 9.3 and 9.5, but we're stuck exactly in this as you described there, where we've taken the Microsoft FTPM implementation, try to run it, and we can access it in U-boot. But then when you actually bring up the system, even if you bring up the modules, you don't see it, or the storage not working.
Yeah, well, there's some, the way systemd works currently, to be able to, to detect that there is a TPM device currently, systemd has two heuristics. One of them is the ACPI table entry for a TPM device, which doesn't exist on system-ready IR usually, only on server-grade hardware. And the second thing is if the TPM device is visible already, which means that you had the kernel drivers built in.
Yes, yeah. But if you step a few points back in it, if you look at what system ready and all these kind of programs are trying to do, they don't get into too much detail there. Is there, and putting all this glue together, which is very, let's say, vertical specific, because in our case, we want to fuse the firmware, we want to secure the bootloader, and then also secure then the operations, the whole chain into it. Because if we can compromise the firmware, then a software-based TPM doesn't make sense. And what I'm finding is trying to put this puzzle together that doesn't fit yet. There's a ton of glue there that just, where do we maintain that?
Good questions. In Linaro, it has been the trusted substrate firmware side from firmware to kernel. And then, we still left the user space completely open. I'm trying to bridge that gap with systemd and with the TPM device there.
Yeah.
And DM-Verity. What we still have is from hardware to the firmware bit, which you are hopefully solving. I don't know where to put these things all together.
Okay. Yeah, I think it's a good question just for anyone in the audience, or it's just a real observation I've seen which challenges us on the receiving end. Yeah.
No, I think we're talking about a lot of TPM details. So if anyone has any other questions, then maybe you can talk on the hallway. But if there's anything else, then I'm happy to discuss. Who's actually doing encrypted partitions on the device right now? Okay, it's a few hands. And you're tying it against TPM then?
Our implementation is using TPM and PKS11 as well, using systemd crypterion role. So, for example, with opti-based devices, or any device with PKS11 supporting there, you can use that, or with TPM, firmware TPM or an actual TPM, you can use that as well. So.
Yeah, I mean the crypton role is exactly this mechanism systemd-repart. It uses the same code under the hood. Okay, great. There are no other questions. Thanks for the attention. Done.